All right, thank you very much for being here. First talk, finally, Pygrunn is back on its feet. Let's talk about AsyncIO. Well, first of all, let me introduce myself if this works. So my name is Òscar. I worked at Pylogic like 10 years ago. That's how I came to get to know Pygrunn. Now I'm working at tickets. We sell tickets for events, and I'm working on automating everything, automating translations, so that we can sell more to more people while working less, leaving the humans to do like the really tricky work that you need humans for. So what about AsyncIO? My first question is, should you use AsyncIO? Who here is using AsyncIO? Can I have a show of hands of, oh, wow, nice. Like 1/3, nice. How many of you are doing like really tricky things, very complicated stuff? Emil is doing it, and Auke. Very interesting. The rest, no. So I think that's very good. I think that's very sane. I was thinking today while I was working here, like, should you do AsyncIO? Well, if you're doubting, maybe you shouldn't. It's a bit like getting married, right? Suddenly, you have to collaborate all the time. You have to yield. If you want to be IO bound all the time, if you want to be arguing all the time, sure, go ahead. So AsyncIO is really good for IO bound things indeed. Why shouldn't you use threads? Well, in threads, the good thing is that most of the time you can pretend that you're just alone. You're just doing your stuff. Whenever somebody needs control from you, you will be preempted, and then somebody else will, some other thread will run. You get to share data. AsyncIO, you have to be very aware of, okay, here I'm going to be IO bound, so I'm going to, now the IO loop is going to take control from me. At some point, I'm going to be called back. You need to make sure that you don't block the loop, that you don't run things that are CPU intensive for very long. So you have to be very aware of what you're doing. So why is it better to run 100 IO loop coroutines than running 100 threads? Well, the main problem here is context switching. Like the system doesn't know if your thread is ready to run or it's still waiting for something. So it's just going to check with it. Hey, can you run, guy? Do you have something to do? But in coroutines in the IO loop is aware of what you're waiting for. So it will call you when you actually have the data that you needed in order to run, when you're no longer blocked. So yeah, it's tricky. It surfaces issues that maybe wouldn't happen in single-threaded. You really have to collaborate. So for me, it feels like it's a very good thing for simple stuff. Like if you can keep it simple, if you have one thing that does only one thing, it's very IO bound, then sure, make that part AsyncIO. And maybe the rest no, or maybe make some other service also an AsyncIO service. Checking my notes here. More important than this is that you can scale horizontally. If you cannot do that, then you're dead if you need to handle more traffic. That's the main thing. So for example, in my case, translations, we don't use AsyncIO. Why? Because I don't have enough traffic. I just run in salary queue in a single process per worker, and that's good enough for me. I could use this as mainly it's IO bound. Somebody asked me to translate something, and then I tell a third-party service to translate it for me. But I don't have enough traffic to have to deal with all these issues. Nice. So I wanted to cover a bit of basics of what is a coroutine, what is a task, what is a future, the three awaitables. Oh, actually, I can change between. So what is the point of a coroutine? Well, you're running, and then your execution will be suspended while you're waiting for something so that some other coroutine can run. And then when you're no longer blocked by that input-output operation, you will get called so that you can run until the next time that you have to yield again. It's similar to a generator. Actually, it's kind of a generator. This is an example of a coroutine. I made here a sample code that, okay, get the local weather. Conveniently, the weather needs the location, which I also need to get from some API, so that's why I'm waiting twice. They're up there in the get local weather. So how does this work? Well, I did here a bit more code that you would normally do, so all the steps are clear. So get local weather. I think I have even a thing there. Yes. So get local weather is not a coroutine. It's a coroutine function. You can call isCoroutine function on it, and it returns a coroutine. And that's the one that you can run in the I/O loop. You could call AsyncIO.run. You can create a task for it, and then you get a task back. So we'll talk in a second what is actually a task. A task for now we know that something that you can await. It's an awaitable. So we await it. We wait for it to run, and when it's done, we have a result, which it was calling these two different functions that are also asynchronous functions and waiting for the results. Indeed. So you can either create a task or you can just await it, which is the same that we did above. Or you could say, well, you told me it was like a generator, right? So can I just treat it like a generator? Sure. You can send none to it, which is actually what happens when you run a coroutine. And then it will raise a stop iteration because there's only one thing that it returns is the result with the result. So that's how it works. Yes, indeed. When you return, internally it will raise a stop iteration. So it's really built on that. If you remember, I think 2016 I gave a talk about Tornado. It was all this kind of stuff. Now it's a bit hidden because it's part of Python, but it's the same thing. So what is a future? The future of what? Well, a future is something that is running in the I/O loop. When it's done, it will tell the I/O loop that it's done. Maybe it will return a result. You can cancel it, and you can assign callback functions to it. Well, this is really vague, but that's the point. It's just anything that is running in the I/O loop. For example, it could be something that is running in another thread. This, for example, is how you would run a function in another thread and still keep track of it in your I/O loop. Let's say that you have all your beautiful I/O loop code, but you need to call one function that is blocking. You don't want to block. You don't want to move that into a separate service, whatever. So you just run it in another thread. This is what this thing does. Let's see. So yeah, I have this count records function, which is very slow from slowdb. I want to run it in another thread, so I call running executor. You can pass it any executor you want. It could run maybe in a celery queue, whatever you can imagine. The default one is a thread pull executor, so this is what this none there does. And it returns something that you can await. So it looks like, hey, it looks like this is an asynchronous function. Like all the complexity has been abstracted away from it, and I can just treat it like any other thing that is running in the I/O loop. Well, you need to be a bit careful with it because almost all the AsyncIO objects are not thread safe. So if you are too happy about what you write in this count records function there, you could run into trouble. Like if you start running things in the I/O loop, because you're running things in the main loop, you're sharing the data. There's this rune coroutine thread safe. There's some thread safe functions that you should use if you are running, if you want to schedule things in the main loop from the function that runs in the thread. And the tricky thing about this is you're not going to notice it if you make a mistake. It's going to work mostly locally, and then in production there's a weird bug. What is going on there? Well, maybe you run into a non-thread safe issue. Let's see. What is a task then? We covered a future, which was something that was running in the I/O loops, vague. A task is the same thing, but something that was running that we didn't know what it was. Here, it's a coroutine. So you don't get to assign to set the result. Futures can set the result. Coroutines, they just return it. But yeah, like when you create AsyncIO create task, well, you get a task that is monitoring this coroutine. Future, as I said, it looks a bit like a promise. I was working in Node.js for a while, so I thought, well, maybe you can use it as a promise. So here I'm passing a future to this function, to this fetcher function, and instead of returning a result, I decided, no, I want to receive a future, and then I will fulfill that future. I will set the result when I'm done. So it also works. Future is awaitable. So as soon as the function above the fetcher function is done and receives the result and assigns it to the future, then the await here, result equals await future, that await will not be blocked anymore, and you will receive the result. I'm not sure you would use it like this, but you can. So Sequentially and concurrent things. There's two ways, right, to run tasks in the loop. Sometimes, like before, when we were checking the weather, we needed to know the location in order to know the weather, so there was no way to run both things at the same time. This is what I do here in this sequential function. As you know, I have a list of coroutines. As you remember, fetch page, async def, that means it's a coroutine function that returns a coroutine. So the list inside of sequential, the list of coroutines, those are really coroutines. I didn't lie to you with the name of the function. And then I just await them one after the other. Await blocks, so only one coroutine runs at a time because I'm awaiting it one at a time. Like the IO loop doesn't even know that I try to fetch pages there. However, in the second function where we're trying to run concurrently, await still blocks. But first I created tasks. I create one task for every coroutine so they can start running there as soon as somebody yields, which is what I'm doing here when I await for it. So await still blocks, but all the tasks get to run. Simple stuff again, but good to be on the same page. Now, I have this function here, this main. I'm awaiting get location. What happens? Like what does it mean? AsyncIO.run, and that does all the magic. What is the magic? Well, we're going to look at the source code of AsyncIO to really understand what's going on there. But first, we're going to look at something that is a bit like the source code of AsyncIO, but it's a little bit clearer so that we can know what really happens. When we have understood this, then I'll jump onto the next slide, and then we will know what happened. So I have 14 things that will appear in the screen. Let's see if I can keep track of all of them. So first of all, AsyncIO.run. We don't even have an IO loop yet. So the first thing is to get the IO loop. This will create or return you basically the IO loop for the current thread. You shouldn't use this function anymore yourself. What you do is you get running loop inside of a coroutine. But you know that's what happens inside of the source code. What am I going to say? So okay, we have now a loop that we can add a task for our coroutine. So yeah, next step, indeed, we schedule the coroutine that we want to run in the loop, and we receive a task. Doesn't work. And here we run until complete, which means just keep running until the coroutine that we were running is done. We are blocked there. There's nothing else for us to do. We were running this function, so this doesn't make any sense to yield to someone. There's nothing else running. So when run until complete is complete, we're done. The task is run, and the loop doesn't have a reason to exist anymore. So now we're going to clean up the loop. And we're going to go into more detail about cleaning up the loop later, because this is a very simple case. So yeah, what do? We get all the tasks that are pending. There were no pending tasks. Well, maybe yes. Maybe this function that we were running created some tasks and forgot to await them. And they are still running somewhere in the loop. So we're going to get all the tasks, and we're going to cancel them. And we're going to look later at what does it mean to cancel a task, and what should you do when you get canceled. Then we wait. So first we cancel everything, and then, okay, those tasks that maybe were running, we don't know, they could be doing something. They could have open files. They could have open connections. They could be serving some customers. Let's give them some time to finish their transactions, if they were responding to a request, finish responding to those requests. Don't accept anything new, but whatever you're doing, finish it cleanly, don't leave mess around. And then when we're done, then we close the loop. Before we stopped it, right? Didn't we? We didn't stop the loop. No, because we needed the tasks to finish running. So now the loop is closed. We shut down the executor. We close the loop, and that's it. All right. So this is the source code of AsyncIO.run, and it's basically the same thing. It just calls a bunch more functions. But if you remember, first we get the loop. We set the event loop with this events thing. We're not going to go into that. And then we run until complete our task that we were running in the loop. And then when that's finished, or whatever happened there, even if it failed, in any case, finally cancel all tasks. We know now what that means. So loop through them and call cancel on them. and then wait until everything is finished, and then close the loop. So pretty clear. But this highlights, like, it's not just running something. There's a bunch of work that is done after you're finished, just so that things are left clean. And that's very important when you're working with AsyncIO. All right, what about testing? Before we go deeper in the tricky use cases of AsyncIO, just one slide about testing. Testing is tricky. If you start to mock things that are asynchronous, it's a little bit complicated. In general, I don't like mocks very much. I prefer to pass things by parameter to dependency injection. Everywhere when there is an HTTP client, there is a client parameter that by default is none, and that means use the default one. And then in the test, I can just pass a fake client. That makes things so much better. So, but there is a PyTest AsyncIO, PyTest-AsyncIO library that lets you mark tests as being asynchronous, and then you have access to the loop. And you can just await things, and it just works. And also, you can define asynchronous functions. If all the tests in your module are asynchronous, you can just mark them all in one go. There's a lot of tricky stuff if you are writing tests and you are like the function that you're testing, they create tasks in the loop. You want to make sure that they all got finished. It's going to be tricky. So there's some resources online. There's not a lot. So good luck. I would advise to keep it as simple as possible, the code, so that you don't encounter these problems. Exceptions. This is something different. That normally when you manage exceptions, let's go back to the when you write code. Okay, I raise an exception. I'm going to accept there, catch it there. It's going to be fine. With AsyncIO, it's a little bit more tricky. So for that, let's imagine the thing I said that I didn't do, that I didn't put translations in AsyncIO. Let's imagine that I did. That I have a queue that receives translation requests. There's a worker that processes them. It calls a translation service. And then when the translations are done, I store them in a translation storage. Doesn't work. I need to walk to the thing. All right. Oh, I put an arrow up because what if it fails? What if translation service is done? Well, I put the request back in the queue, just so that our example is a little bit more interesting. So let's define some data classes for the translation request, the translation task. There's nothing very important here. Just there's what do I put in the queue? Well, the translation request of translate this thing into this language, and I create a little task for myself so I can keep track. Is it done? How many times did I retry this task, etc. We're going to use this in a moment, so I just want you to know what's in those classes. This is my asynchronous translate function. So very simple, right? I receive a translation request. I call a client, call some translate URL. If it works, then excellent. If it doesn't, I raise an exception. We remember that exceptions were tricky, so this is going to open a melon of fun in a second. But if it worked, perfect. We log the info and we return the translation, so everything is fine. Let's see. This is a basic queue worker. I wanted it to put it in a queue so that we had the chance to put things back in a queue and encounter issues there, not just call a function. So let's look at do translate. Very simple. I just get the running loop, and I set exception handler. Why do I do that? Well, there's a default exception handler, but most of the times you want to be alerted, like, hey, there was an exception going on here, and nobody caught it. Is it still fine? Do I need to do something? Do I need to fix something? So it's good to set an exception handler, which I think is in another slide, but I just logged the exception in this case. But you decide what you want to do, maybe depending on the exception. I create a queue, AsyncIO.queue. I'm not going to go into it, but it's not very exciting. You can put things into it and pop them from the queue. And I call schedule translation, which would just put it in the queue so that the worker can work on it. What does the worker do? Well, while it's an infinite loop, it tries to get an extract from the queue. If there's nothing to do, then it's good that it blocks there, waiting for the next task to process. And then when there is a task to be processed, then it schedules it in the IO loop. You could say, but Òscar, IO loop already has a queue of tasks. You could create tasks. Yeah, but I wanted an example that would reveal more issues. Okay, so what happened with that exception? That's what we care about here. That's why there's the little volcano there on the top right. That's what we're talking about, exceptions. So I tried to process a task. That's what I try, because I have a try except block. There's another version without the try except block that I like more. So okay, I'm gonna let's imagine that I don't only want to process a translation request to translate something, but I also want to log the task. I want to do these two things at the same time. AsyncIO.gather, I put there a little screenshot from the documentation, basically just runs both things concurrently, and it returns awaitable objects. So when I'm awaiting, what I receive is, in this case, two variables that are the results of running these two tasks. So the first, translated, is the result of the call to translate, and logged is the result of calling log. If there was an exception in either task, I will have an exception here. Something failed. And then I can retry the task. But what failed? Maybe logging failed, then I don't care that much. But if it translated failed, then I do care. A little bit weird. So maybe like this is better. You see this in the source code as well. They use return exceptions true all the time. Why? Well, in this case, it reminds me a bit of Golang, maybe a little bit more dirty, because in Golang, it's common like you receive the error and the result. Here, you just receive the result, which maybe is an error. You don't know. Same thing as before. Translate and log will run concurrently. And translated and logged, they could be the result of translation and logging, or it could be an exception. So here I can check. And I know what crashed. I know if logging crashed, then maybe I just logged that I could not log, which is a little bit ironic. But if translated failed, well, that's something different. I want to retry. I want to increase the attempts and put the task back in the queue so that I can try later. So it's very nice to use this. It also saves me from an exception being raised in the middle of this. When we're cleaning up, very useful to return exceptions true when we are gathering all the pending tasks, so that we don't have to deal with exceptions there in the middle of that. So that's the trickery of handling exceptions. The default exception handler, I mentioned this before. I am calling this set exception handler. Well, yeah, I just log it here. But it's very good to, it's very easy for exceptions to go unnoticed. Same with signals. So this way, you are aware that some exception was raised. You didn't catch it, so it's logged now. They will not go unnoticed. So to summarize, is it readable? More or less. So more tips. There's this environment variable, Python AsyncIO debug. You set it to 1, and then you will have more information in the logs. Very useful. You can also call loop.setDebug. Then you get more information. If you set log level debug, if you're debugging tricky stuff, there's things that are being logged as warning. Maybe you will not see them otherwise. You can use print stack in the task. If you're debugging a task, you know what is going on, who called it, what state are we in. You can call print stack, and you will have a stack trace of where you are. Very useful. And in the logs, I always watch out for two things mainly. One is when this coroutine was never awaited. That means that I fucked up somewhere. I didn't await. I forgot I had scheduled the task. I lost something. Or something is going wrong there. And this line of executing this task took, that means it was too slow. That means you were holding the loop for too long. By default, it's 100 milliseconds. You can change it if you know that normally you need more time. But that's something to watch out for. And maybe it's not that you're running something that is very slow. You forgot to return something. You got stuck somewhere. You got deadlocked. I don't know. All right. Signals and async generators. I thought tulips were async generators because they all generate their little flower. So that's why we have a tulip up there. Okay, another example. A strange example. We want to download reports from an API, and the reports come one page at a time, conveniently, because then I can have an async generator to deal with them. And then we store it in a file. Convenient, because if it fails in the middle, we don't want a half-broken file. So two things that we have to solve. Okay, async generator. Let me see. we are missing some stuff. All right, so yeah, so these fetch report pages. Well, this fetches a report page by page. Interesting. Conveniently, every time that I call this imaginary API, it returns a link to the next page in the response. So, with these fetch report pages here, what I do is I fetch a page, I yield it, I fetch the next page, I yield it until I'm done. That's an async generator. So here you can see the history of coroutines as generators in the past, because for each value, we're going to raise stop iteration, but when all the loops are, when all the pages have been downloaded, then we'll raise a stop async iteration. And then fetch report page very easily. It just fetches calls on API. So how do you use this async generator? Oh yes, you could actually write the async generator yourself by implementing a enter and a exit. All right. So this is how you use it. You can just async for your generator, and you'll get all the pages one by one. Nice. There's also comprehensions, asynchronous comprehensions. All right, so how does this really work? Well, as I said, you can implement it as a class that implements a enter, a iter, a next. No, sorry, this is a generator. I know what happened before. What I was mentioning is that it was, let me see, I lied to you. Async with, this is a context manager. So I'm not going to go into context managers here, but it's very similar to a non-asynchronous context manager. It's only that you have to implement a enter for asynchronous enter and a exit for asynchronous exit. All right. Yeah, so what happens if it goes wrong? If you download some pages, but then the API doesn't work anymore, it's down, we are going to be left with a half written file, corrupted file. So we really should gracefully shut down. And this is the whole point of all these tulip slides. So, OK, let's define a shutdown function. That's a good idea. We're going to do something similar to what AsyncIO already does, only we're going to do it ourselves. So we have all the control. We know what we're doing. So we have all the control. Oh, this is my timer. Only 2 minutes left. We have all the control, and we to close things. To close things properly, we know what we left over. What we left open. Very important, calling cancel in the tasks, and very important to know what do you want to do when you get canceled. I'm going to go very quickly about this slide. You can look at them later. But yeah, the signals that you have to catch. So for each signal, sigterm, sigint, it could be sighub, many others. It depends on how you're running this. Are you using Docker? Are you using something else? For each signal, we'll add a signal handler, which is just create a task to shut down. And in the shutdown, you shut down whatever you were working on by calling cancel on your tasks. And every task knows what it needs to do to cancel itself. Maybe, as we said before, finish handling the current request properly. There's no hurry, but just finish up. Flash messages and metrics. Here, we're just deleting the file, just as an example. AsyncIO shield. Sounds like a good idea, but actually, it's not that useful. In closing, choose well what you want to run in AsyncIO. Better to keep it simple. If you can just scale horizontally, do that. Be mindful of your exceptions. Make graceful shutdowns part of your happy path. That's part of the job. Sometimes you'll get canceled. Watch the logs for an awaited task, etc. And make your life easy by writing testable code. Here is some resources. Very nice couple of talks by Lynn Root and Andrew Godwin about AsyncIO, tricky stuff, past and future, and a nice book from O'Reilly that covers all this. The images where I got them from. And thank you very much. I think we're out of time for questions.
Yeah, well, there's just maybe time for one small, quick question if someone has a question for Òscar. Oh, wow.
Everything was really clear.
Well, then I guess this was it. Thank you really much, Òscar.
Thank you.
A great talk. And then we have a small present for you.
Ooh.
I'm just going to show you here.
Oh, my God.
This is a levitating lobe.
Oh, my
just,
God.
Enjoy.
It physics. All right. Thanks a lot.
Well, thank you very much. Just for everyone, if you go to another place, you should wear a face mask if you're not in the room. And just, well, get going, I would say.